So thank you for the invitation. I'm Beijiang from IHAB. I'm going to show you the recent results of the observation of an isoscalar resonance with exotic quantum number 1 plus in J-psi related decays to eta1 prime. BESIII got the largest data size in the tau Charmonium region of electron-positron annihilation. This analysis is based on the 10 billion of J-psi. One of the major questions is from the QCD works on the quarks and gluons to the hadron spectroscopy we observed, what is the role of gluonic excitation and how does it connect to the confinement? And the Charmonium decays provide an ideal lab for that hadron physics. So one point is the E plus minus to J-psi have a huge cross sections, so we can easily have clean high statistic data samples. And the J-psi decays, we have well-defined initial and final states, so we can apply kinematic constraints and the quantum number constraints to the reaction. So that will make the analysis relatively simpler. And J-psi decay, the CC bar have two couples to the final state hadrons by gluons. So it's a so-called gluon-rich environment. Especially in the J-psi radiative decay, we can expect a glueball or hybrid, those gluonic excitations have larger production rate than ordinary QQ bar mesons. So one of the motivation of this analysis is about the study of glueball. So we know that from a pure Yang-Mills gauge theory or quantum lattice approach, the expected production rate of J-psi related decays to scalar glueball is at the level of 10 to minus 3. It's relatively a large production rate. And at BESIII, we measured the production rate of F0 1710 and F0 1500 in the J-psi relative decays to KK, pi pi, omega omega, and eta eta. And in most of the decays, we can observe that the production rate of F0 1710 is almost 1 order of magnitude larger than that of F0 1500. And this somehow indicates that the F0 1710 may largely overlap with the scalar glueball, or it could have a large fraction of gluonic component inside. And from the recent coupled channel phenomenology analysis by Bowen group and JPEG, these two work also kind of concludes that the F0 1710 may largely overlap with the scalar glueball. This is for the production properties. So for the decay properties, naively speaking, from in the point of view of flavor symmetry, a pure glueball decays to pseudo-scalar pairs will follow these ratios. And a more sophisticated phenomenology work predicts that the branching fraction of scalar glueball to eta1 prime over the branching fraction to pi pi will be smaller than 0.04. And of course, in this point of view, the decay mode of eta prime and eta prime are very important, so-called missing pieces for the whole puzzle. And because of the low efficiency and the branching fractions, we can only perform the full analysis with the 10 billion of JSI right now. Another motivation for the analysis is about the hybrid. Different from the glueball, the low-lying hybrids have the exotic quantum number 1 minus plus, so which make the light hybrid very distinctive. And currently, the observed candidates for 1 minus plus are isovector, namely the pi1 1400, pi1 1600, and the pi1 2010. It's kind of important to find the partners of the non-net so that we can establish the family of hybrid. And for one thing, the hybrid, as mentioned earlier, it contains gluon inside, so it can be produced in the gluon-rich Charmonium decays, something like this, which is complementary to the ongoing analysis in GlueX, also in the Compass, or in the Compass plus in the future. And it can decays to eta prime in P-wave. There are several theoretical work on that. So for this analysis, the event selection is rather straightforward. The eta is reconstructed by 2 photons, and the eta prime is reconstructed from eta pi pi and gamma pi pi. So we can have very clean and clear eta prime signal. And after requiring the eta prime signal, we got the unit mass distribution of eta prime for the 2 decay mode of eta prime as following. And we have intensively studied the background, and the background level is estimated to be 17% for the gamma pi pi mode and 8% for the eta pi pi mode. So it's a relatively clean sample. And by investigating the inclusive Monte Carlo for the 10 billion BESIII decays, no significant peaking background has been observed. So we can use the eta prime sideband to estimate the background from data in the following amplitude analysis. So for the amplitude analysis, similar as the previous analysis of JSI to gamma eta and gamma kk, the amplitude analysis is based on the covariant tensor amplitudes and performed with GPU PWA framework. And again, we just use the simple isobar models. All the resonances in the eta prime, gamma eta, and the gamma eta prime system has been considered. And the resonance has been parameterized with the relativistic bright weakness. And a combined unbinned maximum likelihood fit is performed for the 2 decay modes of eta prime. Namely, we're sharing the same set of mass, widths, and relative magnitudes and phases. And the background estimated by the eta prime sideband are subtracted from the likelihood. So all the kinematically allowed known resonance of 0 plus, 2 plus, and up to 4 plus in the eta prime system, and the 1 plus minus and the 1 minus minus resonances in the gamma eta or gamma eta prime system are considered, listed in the table. In addition, additional scalar and tensor resonances from the PP-var reactions at crystal barrier and the PS 172 experiments listed in the physics report has been also tested. And another scalar resonance, the F0 1810, which has been observed in J-side decays to gamma omega phi, has also been included in the pool of possible resonances, because sort of omega phi is similar as eta1 prime in terms of the flavor symmetry. And we tried all the possible combinations, and we only keep the resonances with the statistical significance larger than 5 sigma. We got the so-called PDG optimized set of amplitudes. The mass of width of the resonances with large phase fractions has been further optimized with respect to the PDG values. And for those resonances close to eta prime threshold, and for those resonances with small phase fractions are fixed to the PDG values. So this is why we call this set of amplitudes is so-called PDG optimized set of amplitudes. And this set of amplitudes can fairly well describe the data, and as you can see, like this. And these are the mass spectrum of eta prime and gamma eta and gamma eta prime, and the helicity angle of the eta in the helicity frame of eta prime system. And based on this, we perform a scan for the new resonances. Namely, we add additional resonance with certain quantum number and mass and width in the previously mentioned wave set. And we evaluate the significance of the additional resonance. And these plots shows the change of likelihood by adding a certain additional resonance. And we can see that significant additional contribution with quantum number of 1 minus plus is shown in this figure. The other contributions are other additional contributions, the significance are smaller than 5 sigma. And this one, the 1 plus minus in the gamma eta prime system is somehow close to 5 sigma. This has been also investigated. But if we add the additional 1 minus plus in the amplitudes, in the sets of amplitudes, this 1 plus minus in the gamma eta prime system, this additional contribution becomes no longer significant. So by introducing 1 minus plus signal in the wave set, we re-evaluate the significance of all the contributions, and the some of the contributions in the PDG optimized wave set become insignificant and are omitted from the selected wave set. And the significance of F4 2050 is reduced from 5.6 sigma to 4.6 sigma, and it is still retained. So this is the measured mass and width and the branching fractions and the corresponding significance for each component in the baseline set of amplitude. And comparing to the previously mentioned PDG optimized wave set, the likelihood of the baseline set is improved by 22, and the number of free parameters is reduced by 16, which means that we only need less components to have a better description of the data. So the baseline set of amplitudes has been preferred. This is again the partial wave analysis fit projections, like comparison of the partial wave analysis results to the data. We can see all the distributions have been well described. And this page shows the comparison of the Dulles plot of the partial wave analysis result and the data and the set band. And basically, the partial wave analysis result can reproduce the features of data. And this page shows the fit fractions in the partial wave analysis fit, and with the baseline set of amplitudes, you can see each contributions and the interference between them. This is for the observed event. And for the additional resonances, we have evaluated all the additional resonances, and the significance of those resonances are all smaller than 3 sigma, as mentioned earlier. And in this case, if we assume the eta1 1855, the 1 minus plus is a additional resonance, and a scan we perform a scan of the eta1 with different mass and bases, you can see a clear exceed of 5 sigma, around 1.8 GeV. And if we try to have another 1 minus plus contribution in the fit, and the other one, the additional 1 minus plus will have a mass around 2.2 GeV, but it will have a very small fit fraction. Well, the significance is not so small, it's 4 sigma, but the fit fraction is 1 order of magnitude lower than the eta1 1855. So we don't include another 1 minus plus in the baseline set of amplitudes. So we also perform the search for other additional contributions with different spin parities. And we can see there's no additional contributions here. Again, as mentioned previously, if we have a additional 1 minus plus, significance will be around 4 sigma, the mass is around 2.2 GeV. And we have some further checks on the exotic state eta1 1855. So firstly, we change the spin parity of the eta1 1855 to other possible spin parities, and the likelihoods are worse by at least 200 something units. So we are pretty sure about the spin parity assignment of the eta1. And we also try to investigate the Breit-Wegener phase motion of the eta1. So we change the complex form of Breit-Wegener to a real one, and the significance, the likelihood is worsened by 43 units. So which means that we kind of not only observe a peak here, we also need a significant Breit-Wegener phase motion here. And another further check is looking at the angular distributions. So we divide the United mass of eta prime into 3 regions, and we can see that in the middle plot, the angular distribution shows a clear asymmetry structure, and it is largely due to the eta1 signal. This feature can also be expressed in another way. So the angular distribution can, as a function of eta prime inertial mass, can be expressed model independently in terms of Lorentz polynomial moment. So basically, for each bin of eta prime, for every event, we weight this event by the Lorentz polynomial moment as a function of cosine theta. And of course, for data, the weight equals 1, and for the background subtraction, we have a negative background. So this is for data. So we can have the dots with error bars are the background subtracted data distributions. And for the Monte Carlo, to make the partial wave analysis results can be compared with data. So we use the phase space Monte Carlo distributions, and for each event, is weighted by the intensity calculated in the partial wave analysis. So we can have the partial wave analysis result can be compared with the data directly. So if we ignore the contribution of from the gamma eta or gamma eta prime spectrum, and these so-called angular moments can be interpreted in the following way. What we need to pay attention to is the y01 moment. This one. This one is corresponding to the p wave contribution in eta prime. And normally, if you don't have the exotic quantum number, you only have 0 plus, 2 plus, 4 plus, and this term will equals to 0. And of course, there are contributions from gamma eta and gamma eta prime system. We can see that even we exclude the eta1 in the partial wave analysis result, we can also see the blue curve contributions. But however, the magnitude or the strength of the structure in the angular moment of y01 is eventually driven by the signal of eta1. So this is kind of a proof.
Beijiang, you have 2 minutes.
Okay, yes, I'm almost finished. Yeah. So this one is kind of direct proof that we need a 1 minus plus here. And for comparison, we make on the left panel of this page, we show the baseline set of amplitudes, the angular moment distributions here. And we also show the previously mentioned the PDG optimized set of amplitudes. We can see in again in the y01 angular moment, we can see even with a lot of contributions in 1 plus minus or 1 minus minus in gamma eta and gamma eta prime system, this structure cannot be described. So we perform a comprehensive systematic studies of this analysis. We perform this page shows the systematic uncertainties for the event selection. We consider the tracking, the photon detections, and the kinematic fit also, and the 2 decay modes of eta and of eta prime has been combined with the weighted least square measure. And for the amplitude analysis, we consider the parameterization of F0 1500 because it's close to the eta prime threshold, and we replace it, the Breit-Wigner, with a Flaty-like form. Eventually, this doesn't change a lot because the coupling is very small. And for those resonances fixed to the PDG values, we're varying those parameters within 1 standard deviation. And we also try other alternative fits with different background estimation. And we also investigate the influence of the additional resonances by adding those most significant additional resonance of each possible JPC into the baseline fit individually and repeat the whole analysis. And in all the alternative fits, the 1-plus signal is always very significant. The significance is larger than 19 sigma. So this is summary. An isoscalar 1-plus eta1 1855 has been observed in J-psi related case to gamma eta prime with significance larger than 19 sigma, and the mass and width and branching fractions are measured like this. But up to now, we don't know whether it's a hybrid, a molecular, or a tetraquark. We should investigate other decay or production mechanism and search for other partners in more reactions. And furthermore, significant J-psi related case to F0 1500 to eta prime has been observed, while this F0 1710 is insignificant. So we have the upper limit at the 90% confidence level for the branching fraction of F0 1710 to eta prime over it to pi. The upper limit is 1.6 times 10 to minus 3. Remember, the theoretical prediction for glueball is smaller than 0.04. So this kind of support the F0 1710 has a large overlap with the glueball. So that's all. Thank you.
Thanks a lot, Beijiang, for this very nice and clear talk. Time for question. Søren raised his hand. Please go ahead.
Thanks very much. It's of course a very important.
Can't hear you.
Please make more loud your voice.
Yeah, it always goes back. Is that better? Wait a second.
No.
It was for the first second.
Yeah, try again. Søren, can you hear me?
Yeah, I can hear you. I can hear you.
I can hear you very loud now. So go ahead with your question.
Okay, now, okay. Sorry, it always adjusts itself, the volume. Thanks very much, because I think it's a very important observation. My question is the following. So why is it so difficult to see that state? And I think the answer is because of this, the activity of the 0++ and 2++ in that region, yeah, the around 1800, which is very strong. Yeah. So my question would be, you are including resonances, known resonances up to 4++. And they are in the same region, and that's why it's so difficult to distinguish. In S wave, they are there, while your state is in P wave. Is it possible that this wave is instead a 6++, which you're not including in your default fit? Maybe a stupid question.
A quick answer is no, because you have to have an even number, an odd number of spin. So it's either 1 or 3. You cannot have 6 doesn't help. 0, 2, 4, 6 doesn't help for this distribution.
Okay, yeah, thanks.
Then I see Christoph.
Hi, thanks for the nice talk. Actually, my question goes in a similar direction. When I look at this upper right plot, I see that the partial waves you are already including is indeed capable of producing a peak right in the correct position. Therefore, to get a structure at this point doesn't necessarily require an additional state. On the other hand, what you are using as the model for the non-exotic stuff is adding Breitwiegners. Adding Breitwiegners by construction, when they overlap strongly as they do in the 0++, has the wrong phase motion because unitarity is severely violated. Therefore, can you really exclude that what you are observing here as a state is not an artifact of the amplitude model? And alternatively, would you aim at, for instance, trying some K-matrix fit? Because we've also seen in Bertram Koff's talk, for instance, that taking Breitwiener parameters from one reaction to the other is dangerous. And therefore, maybe your S wave is simply not correct. Thank you.
Yes, thank you for the good suggestion. And the answer is yes. For our second question, the answer is yes. We do have the plan to perform a couple channel analysis for all the J-side related decays to the pseudo-scalar pairs, which includes the pi, kk, eta prime, and eta prime. And it's kind of on the top of our to-do list.
I'm happy to hear that. Thank you very much.
And for the first part, my point is, indeed, we try to add more resonances in the wave set, and it cannot reproduce this say narrow structure in the P-wave system. Again, you are correct that the description of S wave is not, in principle, it's not correct due to the violation of unitarity. And if we record the other analysis of J-side relative decays to K short, in that analysis, we have two approaches in parallel. One is a description with a sum of Breitwiegners. The other one is a so-called model-independent approach, just to detangle the different contributions from 0+, 2+, 4+ in each bins of KK. And finally, in the end of the day, the description, the shape of the scalar contributions in the Breitwiener-based model-dependent fit is in a very good agreement with the model-independent S-wave approach. So it's kind of tell us that as long as you have more resonances in your fit, at least you can have an effective description of the data, even though the resonance parameters extracted from that sum of Breitwiener is not correct, but you can have a fairly well description of the S wave. This also tells us that so you can have a fairly well description of the S wave, like we showed here in the other plots or the D wave distributions, but you cannot describe the P wave here.
But do you know what produces this peak at the exactly this eta1 mass? Because you don't have any P wave in at the moment.
It's from H1 and rho or phi signal.
Okay, thank you.
Yeah.
We have just two quick questions, one Biplop and then Eulogiu. Biplop first.
Yeah, yeah. So on this plot, I find it a bit weird that you only, so you were saying that this. Okay, so basically, my point is that, if you're taking out is the difference just because you do not have the P wave in the blue curves, and if you do have the P wave in the red curves, is that correct, or is it you also have a P wave from other components in the blue curve or not?
Oh, no. The point is, let me repeat it in a better way. So the distribution of the data itself is model independent. It's just the event weighted by the Lagrange polynomial. And for this upright plot, if we ignore the contribution from gamma eta and gamma eta prime, it will be a pure P wave in the eta prime system, like shown in the bottom left formulas.
Right. There
And we do have the contributions from gamma eta and gamma eta prime, as just Christoph just mentioned. We have H1, we have rho, we have omega or phi in the gamma eta or gamma eta prime signal. So even we don't include the 1 minus plus in eta prime system, the blue dashed curves can also have a structure here.
right. What I'm trying to say is that if from the top right plot you're saying that there's a large P wave, why doesn't it show up in the other plots as well? Because there are other P terms. For example, the 0,0 component also has a P square, and there are other, so why doesn't it show up elsewhere? That was my point as well.
Because of the phase fraction, the P wave is eventually a smaller contribution. I mean, the differences between the red curve and the blue curves in other plots also exist, but they are not quite visible.
Okay, it just seems quite striking. Yes, I understand your point. It still seems a bit striking. Okay, thanks.
Biplap, maybe we can move to the discussion in the afternoon. Last very quick question from Eulogio, and then we have the coffee break.
Okay, I mean, I was wondering, whether you could do the same reaction. I mean, instead of producing a photon, producing omega or phi. The quantum numbers, you still would get in eta prime, you still get the same quantum numbers.
Exactly.
That will give you different phase space, which I mean might help. I mean, some of the equations we are discussing here. And also, I mean, the phi and the omega having, I mean, different flavor quarks might also give you some insight on what is the nature of that peak that you see. I don't know what you have thought about.
Exactly. Thank you for your suggestion. And eventually we do have those ongoing analyses. People are currently working on that. Yes.
Okay, very good, very good. And then, if you allow me, now it will be less than 1 minute, half minute. One comment you made at the beginning, I'm not so sure that you just made a comment that the F0 1710 was largely, I mean, had large overlap with the scalar glueball. Well, might be or might not be, but I mean, I want to call the attention that this resonance, I mean, appears very naturally in the work of Li Shengeng and collaborators. I mean, as a K star bar, I mean, in a couple of channels, I mean, and it has been tested in many reactions. It has been tested in many reactions, including the latest one also from BESIII, the DES going to pi plus K short. And so, I mean, it has passed many tests there. So, I mean, on the other hand, the F0 1500, I already said the other day, we don't have any idea what this can be. It's very narrow, very narrow. The width is only 100 MeV, and the F0 1370 has a width of 400 MeV. So this one is the strange. The strange one is the F0 1500. This is the strange one. Who knows what it is?
Okay, thank you for the comment. And I do notice that the possible interpretations of F0 1710 as a molecular state of K star bar. My point here is from the production property and the decay properties, the results kind of support the it has a fairly large gluonic component.
Okay, well,
but we cannot exclude the possibility of F0 1710 is a K star molecule.
Yeah. Okay, good. Thank you.
Thank you, everybody, for the nice discussion after the talk, and I hope it will continue also in the afternoon. For the time being, we close the first session of the morning, and we reconvene at 11:50 now for the second part of the morning.